Hello everyone, and welcome back to another episode of my AP Calculus series. Today is Mother's Day. I doubt I have any mothers watching me right now, but if you're out there, thank you. I support you in all your endeavors, and I hope you have a great day. But back to the content. In the last episode, we finished up talking about the three methods of evaluating limits, which were by tables, graphically, and analytically. Analytically being the most important in my opinion. But so far we've only been talking about the processes of finding limits, not their actual applications. Today we're going to be diving into one of the most important applications of limits, and that is with continuity. We can use limits to show continuity at a point and also over an interval. I also have this spiffy metal bar that I can use to point at stuff, and it can also be used as a defense mechanism, just in case there's any kind of evil integrals or something trying to attack me during these videos. So I'll have that here just in case. So today we're going to talk about how we can use limits to show continuity. So let's use this function as an example. Let's come up with a few standard characteristics a function has to have for it to be continuous at a specific point. Today we're going to be talking about this theoretical point x equals c. At x equals c, excuse me. Teachers just went crazy because I said x equals c as a point. But at x equals c, excuse me. Let's come up with some basic guidelines that we could use to test if this thing is continuous or not. So the first thing we need to consider is, does f of c exist? So f of c has to exist before we can show any kind of continuity. Because if there's no point f of c, then we can obviously tell that there's just a hole and it's not going to be continuous. Although here we do have a defined point at f of c, just not making it continuous. This is really important. We're going to get into that next. This right here would weed out functions like f of x equals 1 over x squared, where you have the asymptote here. It wouldn't be continuous right here, even though it looks like it's kind of approaching the same thing from both sides. It would also weed out a lot of other types of functions with asymptotes, but I'm not going to mention every single type here. We need to move on. So this thing still passes our test, even though it's not continuous. So we need to come up with some more proper guidelines to make sure we're covering everything. A second thing to consider is that, is the function approaching the same value from both sides? Because if we have a function over here, like this, I've been using this one a lot, the x over absolute value x function, or vice versa. This one, it's approaching two different values from the two different sides, so therefore it cannot be continuous. How will we write that in words, though? We have been talking about these things called one-sided limits. I kind of got ahead of myself. That didn't actually appear until this section of the book, 1.4, but it's coming up in a real important way right here. Our second thing here is going to be that the limit as x goes to c from the left of f of x is going to equal the limit as x goes to c from the right of f of x. Meaning that the limit as x goes to c of f of x exists. Because this part right here is a requirement for the limit to exist. The left and right hand limits must be equal for our limit at the point to exist. In this case, it still passes our test because the limit is going to be the same from both sides right here. It's approaching the same point. And we did weed out some types of functions here, like the x over absolute value x, but there's still a lot more things that we need to cover other than just those jump discontinuities. What if we have like a hole here and a defined function functional value up here, we still need a third condition to make sure that functions like this don't slip through the cracks. So our last thing is going to be that the limit as x goes to c of f of x must equal the functional value at c. And this is really important because this is the condition that weeds out functions like this that have a hole but also have a defined functional value, because the limit here you can see is down on this main part of the curve right there, but the actual functional value is up here. So that's how we can show that this one is not continuous. This set of things right here is known as the three-part continuity test for obvious reasons. There are many different ways of showing this three-part continuity test, but for me, this set of three basically covers everything. You could also have an extended part 3 that just states that the limits from left and right both equal the functional value. That would work as well, but I don't really find it necessary because you already showed that the limit exists here, meaning this part is kind of unnecessary. But if this is what you like, then go with it. This is like an either or situation kind of here, because if this limit exists, this has to be true anyway. It's just a matter of preference, in my opinion. So that's the three-part continuity test. Use this to show if a function is continuous at a point or not. It will always work, and you can fall back on it. These continuity restrictions are going to be really important moving forward, because in calculus, especially in chapters 1, 2, and 3, there's a lot of things having to do with derivatives where continuity is required to show something else down the line. So if you don't know how to establish continuity, you're going to be in a world of hurt for that. So make sure you have this basic idea down and know what's going on. There's one more basic idea in this section, which is, I wrote this key points thing over here just so people can use as a reference, and I can use as a reference. But the next thing that we're going to be talking about is the intermediate value theorem, also known as the IVT, which also requires this continuity to be stated for it to work. So let's erase what we've got here. Actually, we could do it below. Let's do that. Let's do the intermediate value theorem down here. Also, in a previous video, I believe I wrote TH period. That's just an abbreviation for theorem. So if you were confused on what that abbreviation is, that's all it is. It's nothing special. I just get tired of writing the word theorem over and over again, so that's how I do it. I learned that from my 7th and 8th grade math teacher. So, okay, so that IVT, let's show it on the graph up here first. If we have a continuous function, it must be continuous. Let's leave a little gap here for now. Let's call this point right here A. Let's call this value right here B. And then put points in. Okay, let's say that we know this function is continuous. But we don't know what's going on with the function in here. We know that the function has to pass through this area somehow to get over here, but we don't know how. We want to show that this function at a certain point reaches a value, let's say right here. Let's call it f of c. This c could be anywhere in here, by the way. We don't know where. We want to show that f of c, we want to show that the function somewhere has a value of f of c between a and b, and we know it's continuous, but we don't really know how to show that. So the first condition that you have to have is that for this IVT theorem to work, for the intermediate value theorem to work, you have to say that your function f is continuous on, I believe, the closed interval AB, meaning including the endpoints. I'm going to check on that just to make sure. Yes, I'm right. So your function f must be continuous on the closed interval AB, meaning from x equals a to x equals b, including those endpoints. These square brackets represent including the endpoints, and these normal parentheses style brackets are excluding the endpoints. That's something important to know if you haven't covered interval notation in your pre-calculus classes. So this is what is called inclusive or a closed interval. This notation right here is known as exclusive or an open interval. You'll see these words closed and open a lot in AP Calculus, so this is really important to know. So first condition, this is really important that you state, f is continuous on AB, closed. So if we know that f is continuous on that interval AB, no matter what little line that you draw, whatever function you try to make through here, the line will always have at least one point that crosses through f of c. Like, oh, I made this a little bit too high. I'm going to make it lower because the b is right there. Let's put it like there. Sorry about that, guys. So no matter what line that you draw, the function is going to pass through f of c, because f of c is between f of a and f of b. We could show that right here by putting our little f of b and f of a in there. So if we know that since f of c is between f of a and f of b, that there must be a point c in here between a and b that causes that functional value to come out, how do we show that? How do we prove that that's true? Well, that's what the IVT is for. It basically states that on any path between these 2 points, there has to be at least one. There could be more than one. There could be any number. But there has to be at least one point, x equals c, such that the function will output f of c, which is the value that you have right here. So basically what the IVT states is that for a value x equals c, c is less than b but greater than a, there is at least one value c such that, okay, let's see. Oh wait, for a value x equals c, given that, I'll just say given, and f of a is less than f of c is less than f of b, there is at least one value c such that, I should also, well, it's given that, so I'm not going to say in the interval. Here, instead of putting given that, you could also say in AB, such that f of c, such that the value f of c is outputted. Another way I've seen this written is with k right here. Like you put k. This is the preferred way of doing it, actually. You put k there, and then f of c equals k. So basically what this means, I'll decode the language. For a value x equals c, there's okay, excuse my blabbering, but there is at least one value, x equals c, in here, such that the function will output k, given that k is between the two vertical bounds of the function. Like right here at f of a and right here at f of b, there has to be a place on the function that passes through f of c, which we're calling k. There has to be at least one value. Why does it say 1 ONVE? Excuse me, I just had a stroke. 1. At least one value c in AB such that f of c is equal to k. This is just putting into words something that is basically common sense. This is what you'll use to prove that the function does hit that point at least once in its runtime. So another really important application of the IVT, I want to show that really quick before we end off for today. A really important application of the IVT. If you have a function that looks like this, let's say we have this, but we don't know what's going on in between here. You may get a function like this, and then have, let's say this is 2, let's say this is 3, let's say this is -1, let's say that this is 1. So you could have a question on an exam or something that says, using the IVT, or they may not even be nice enough to say using the IVT, but prove that this function f of x has a root at x equals c, given that c is less than b is less than a or whatever. Or prove that f of x has a root in the interval 2, 3. That would be the most common way of putting it. So if you are asked to prove that f of x has a root in 2, 3, how are you going to do that? Well, you can use the IVT. You know that there has to be a point where it crosses the x-axis in this area, no matter what function that you draw. If it's continuous, then there must be a way to show it. And that's what the IVT does for us. So the first thing you have to say every single time is that since f of x is continuous on the closed interval 2, 3, this would have to be either given to you in the problem, or you're given something like a polynomial, which is always continuous everywhere. You always have to have this continuity statement at the beginning, or else they're going to get really mad at you and take points away. AP graders are looking for reasons to take points away from you. You need to cover your bases as much as you can. So make sure you have this continuity statement there. Since f of x is continuous on the interval 2 to 3, closed, therefore, by the IVT, this 3 dots thing means therefore, by the way. That's a really common notation and very helpful to use for timed exams or any kind of writing in math. It's very helpful because you don't want to always be writing therefore and theorem and stuff like that. It's always those TH words that get shortened, but okay. Since f of x is continuous on the closed interval 2 to 3, by the IVT, since 0 is less than f of 2, which is less than f of 3, meaning that 0 is between these two functional values. This one would have been minus 1, and this one would have been 1. We're going to say that k is equal to 0 in this case. You don't have to write that, but we're pretending that this is our k right now. I'll draw a line to show where this problem is. By the IVT, since 0 is between f of 3 and f of 2, there must be a value x equals c, given that c is less than 3 but greater than 2, because somewhere in here is going to be a c where there's a root, where if you don't know what a root is just a 0, a point where the function crosses the x-axis. There has to be at least one point c where the function crosses the x-axis by the IVT. There must be a value x equals c, given that 2 is less than c, but c is less than 3. There must be a value x equals c such that f of c is equal to 0. And if you have an f of c equals to 0, therefore there is at least one root. I should have at least one in here, because there could be more than one. There should be at least one value x equals c, such that f of c equals 0. Therefore, there is at least one root in this interval. Boom, done. You just showed that there was a root in here without knowing what the root is, without knowing where the function goes. It could go like this for all you know. You have no idea. There could be 3 roots. There's no way to know unless you have what the function is, or you have time to guess points, or you have a graphing calculator or whatever. The IVT will help you do that. If you can find a point where 1 is greater than 0 and 1 is less than 0 for the functional value, you can always prove that there is a root there, as long as the function is continuous on that closed interval. You need to have the continuity for this to work, because if you don't have continuity, you could have something that looks like this, and you play yourself. Let's see here. You could have something that looks more like this. You could have a hole, you could have an empty space in between, and then another hole. And then there's no root there. You just said something that wasn't true, because you didn't know if it was continuous or not. But if it is continuous, the IVT will still apply. Sorry for all these rants and tangents, but this information will help you a lot on your AP exam. This is a really important application of limits that you should get down cold and be able to do this very quickly. Be able to write out this IVT statement, practice writing the IVT statement, do problems with it, because it'll help you a lot in the long run. I think that's about it for this section. We're almost done with chapter 1. Isn't that surreal? Chapter 2 is a lot of fun, so I'm excited to get there. But we have, I think, one more lesson left, which is going to be on limits at infinity, I think? Infinite limits. So we'll be getting into that next time. Thank you guys for watching. As I said, happy Mother's Day. Hope you enjoyed. I'll see you guys next time.